Before 2020, designing neural networks relied on trial and error. Engineers used intuition and guesswork to determine how deep a network should be, how wide its layers should stretch, and how much data it needed to process. In 2020, Kaplan and colleagues at OpenAI proved that language model performance follows a predictable mathematical function of scale. This log-log plot demonstrates their primary finding. The cross-entropy loss drops in a clear, linear trend, governed by three strict constraints: non-embedding parameter count, dataset size, and total training compute. These precise mathematical power laws hold true across 6 entire orders of magnitude. While these laws provided a reliable compass for research, the initial conclusions regarding how to divide a limited compute budget contained a mathematical flaw. That miscalculation justified an industry-wide race to build massive language models with hundreds of billions of parameters that were left starved of training data. To see how the industry course-corrected, we'll analyze the underlying power laws, the mechanics of critical batch size, and the 2022 Chinchilla correction. The most critical variable in this equation is n, the non-embedding parameter count. These are the weights in the attention and feed-forward layers that perform the computational work, excluding vocabulary lookup tables. For a standard transformer decoder, n is approximated by multiplying a constant of 12 by the number of layers and the square of the hidden dimension size. As long as n is held constant, the actual shape of the model is irrelevant. Whether the network is deep and narrow or shallow and wide, the final cross-entropy loss remains statistically static. When resources like compute and data are not acting as bottlenecks, the final loss is dictated by 3 specific empirical power laws. Scaling with model size follows a power law, where the loss decreases with an exponent of 0.076. Scaling with dataset size d is governed by an exponent of 0.095. When compute is optimally allocated, the loss decreases with an exponent of just 0.050. These fractional values result in incredibly shallow curves. These tiny exponents guarantee severe diminishing returns. Linear improvements in performance require exponential increases in raw scale. This dynamic creates sample efficiency. Because massive models sit further along the scaling curve, they extract more signal from every individual token they process. If a large model and a small model target the same level of performance, the larger model will reach that goal in fewer training steps and with less total data. Those power laws describe scaling under ideal conditions, but a finite training run on physical hardware requires calculating a total compute budget. Total non-embedding compute is approximated by the formula 6NBS. The 6N represents the operations required for a forward and backward pass per token. That base cost is multiplied by the batch size and the total number of update steps. Engineers manage training time by adjusting the batch size, but the critical batch size is a dynamic limit. It dictates how much parallel data a model can efficiently absorb at its current stage of learning. Critical batch size is determined entirely by the model's current loss. Charting this reveals that the exponent of 4.76 creates a steep exponential outward flare on the horizontal axis as the loss drops. At the start of training, when loss is high, the model learns rapidly from a narrow stream of data. Using massive batches at this stage yields redundant gradients and waste compute. Near convergence, as loss drops, the remaining gradients contain higher variance. To compute accurate updates and refine performance, the optimal batch size expands massively. Maintaining efficiency requires continuously scaling the batch size upward in lockstep with the model's performance. Given a fixed compute budget, researchers must decide what percentage of those flops should expand the model size and what percentage should process more data. Kaplan's team attempted to solve this by minimizing the combined loss function against a fixed compute constraint. Their analysis suggested that as compute scales, model parameters should scale at a rate of c to the 0.73, while data should only scale at c to the 0.27. This allocation heavily favors increasing the physical capacity of the architecture over processing more tokens. This logic encouraged the industry to build models with hundreds of billions of parameters while deliberately stopping training runs early. At extremely high compute limits, the empirical data began diverging from Kaplan's predictions. Kaplan's team used learning rate schedules that decayed over a fixed number of tokens, which penalized models that could have effectively trained on much larger datasets. In 2022, Hoffman and the team at DeepMind published Training Compute Optimal Large Language Models, providing the definitive correction to the scaling error. Their revised analysis showed that model size and dataset size are equally vital. To be compute optimal, parameters and data should both scale at a rate of c to the 0.5. To minimize loss for a given budget, parameter count and dataset size must increase equally. Kaplan correctly identified the predictability of scale, but underestimated the volume of tokens required to properly saturate those parameters. Translating the c to the 1/2 power rule into production engineering provides a clear operational heuristic for training. The compute optimal scaling ratio is 1 parameter to approximately 20 tokens. For every parameter added to an architecture, the training dataset must increase by 20 tokens. A billion parameter model requires at least 20 billion tokens of data to justify its compute cost. Despite this correction to the allocation of resources, Kaplan's foundational axiom remains intact. Transformer loss is still a predictable output of model size, data volume, and compute. The specific architectural shape is still a secondary factor. This correction drove the development of highly capable models with smaller parameter counts, such as Llama, by shifting compute back toward data. The governing math hasn't changed. We have simply refined the balance between model capacity and data volume. Ultimately, modern language models reach their absolute peak performance not through guesswork, but through the precise mathematical equilibrium of scale.